Welcome to this episode of the Machine Learning LightPod of the Laboratory of Process Automation Systems. My name is Felix Fiedler, and today we are going to talk about the topic Principal Component Analysis, or PCA. And as always, I'm here with Professor Sergio Lucia. So welcome, Sergio.
Yeah, thanks for having me here.
Yeah, Sergio, PCA, an important topic in machine learning. Can you explain to us when you would use PCA and for what kind of problem you would use it?
Yes, so Principal Component Analysis, or PCA, is a typical technique for what we call dimensionality reduction. Yeah, what does it mean? It means that we can use PCA when we have large amounts of data with many different dimensions in the data, and we would to find out, okay, which are the most important parts of the data? Is there something we don't have to use to actually achieve our goals, such that we can be, for example, more efficient?
Right. Sounds a bit abstract. I would say we have a look at an example and hopefully then it becomes a bit clearer what that means.
Yes.
So, Sergio, what are we seeing here?
Exactly. Here we see a good example for PCA. Yeah, you can see here that we are going to have different features that we have collected for different samples. Yeah, what are these samples? So the samples are basically different scores for different countries. Yeah, and these features and scores are the following. Yeah, so we have different features. For example, the GDP per capita or the healthy life expectancy. Freedom to make life choices, etc. And the idea of this report was basically to find out whether these features here can explain some happiness score that was also reported. Okay?
Right. But the goal of PCA is not to give us some sort of regression model so that we can compute some output like the happiness score, but it is about working with the features, the inputs basically. And what do we want to do with these inputs?
Exactly. So we want these are the inputs. So from here until here, those are the 6 features. There are 2 that are missing because we don't have enough space. Yeah. But these are the inputs of the data that we have, and we would like to find out is what is the best possible way to represent this data such that maybe we don't need all these full 6 features. Maybe with 1 feature or 2 features, it is enough to actually work with those features and do a prediction of our score or do any other task that we want to do with those.
Yeah, so I mean, in maybe naive approach to deal with this problem would be to just drop some of the features. Maybe just say, maybe the healthy life expectancy is the most important feature, and if we know that, we can, in a later step, predict the happiness score. Right?
Exactly. That would be a very simple approach, but maybe it's not the best one. Yeah, let's have a look at exactly if we do exactly that example. Yeah, you see here on the x-axis, you see that feature, healthy life expectancy. On the y-axis, you see the score. Yeah, and you see that, well, there is indeed some correlation. So, well, of course, the healthy life expectancy is correlated to the happiness score, but this is not a perfect explanation of it. For example, for the same healthy life expectancy, you have a very big deviation or a very big variation for different values. Yeah, so you cannot only explain with this feature the full score. Yeah.
Yeah. I mean, it makes sense. If I just naively drop 5 out of my 6 features, I lose a lot of information intuitively. And also, how would I know which 5 features to remove? I would have to try all of them, and maybe with high-dimensional data, this wouldn't even be possible.
Exactly.
So I guess there's something smarter that we can do.
Yes, you can do many things, yeah, but maybe one possibility that is also what will be done within PCA is, okay, maybe we can have, for example, a linear combination of some of the features that try to explain better the data, and maybe we can try to achieve the best possible linear combinations, and this is the motivation of principal component analysis.
Right, so we have an example here for where we did such a linear combination, exactly, and this linear combination takes into consideration the original features, but it basically puts them together in a new, let's call it feature, by multiplying it with different weighting factors or values, and then just summing them all up.
Exactly, yeah, we have a new feature, and this is a single feature, yeah, that we call XPC1, yeah, the notation will be clear also later, which is just, as you said, it's just combining, doing a linear combination, yeah, so it says, okay, I am going to multiply by the factor 0.5 the GDP per capita and add to 0.5 of the social support, etc., etc. And we can then form a new feature, which is different than it's a linear combination of the previous one, but it's only one, and it can describe our data much better than maybe one single one. Okay, but we still have the same complexity. We only have this dependency depending on only one single feature, but we can achieve a better fitting or a better classification, whatever our machine learning task is afterwards.
Right. So the question now is, how do we get these factors? Where do these come from?
Exactly, and this is exactly what PCA is about. Yeah, we want to compute the best possible factors that are going to help us in building our data compression technique or our dimensionality reduction technique.
Right. So I would say at this point, let's introduce the mathematical setting. And then in the next step, we are going to introduce the algorithm of PCA.
Exactly. So what's the mathematical setting? And as we said, when the setup that we have is basically, we are going to start with a data matrix. Okay, this is all that we actually need to do PCA. Yeah, we start with the data matrix, and we are going to denote this data matrix with X bar. Okay, and X bar is going to be a data matrix, as we said. Yeah, so if we draw it abstractly here, we are going to have several data points and several features. Yeah, so we would have m samples, and we will have n different features.
Right. And if I just project this back onto our example, so a sample would, for example, be Finland or Denmark and the associated values, and then the features would be starting from GDP per capita all the way until freedom to make life choices, these 6 features.
Exactly.
Right.
That would be our data matrix.
And we ignore the score for now because we don't care about the score for PCA.
Exactly. Score will be Y, so the output in our machine learning task that maybe we want to do after that. But principal component analysis deals with the data, with the input data
Right.
that we would have in our typical machine learning model with X.
Right.
Okay.
Perfect. So at this point now, we can introduce the algorithm of PCA. Most of you might have already seen it. And in a later step, we will then, and this is the goal of this machine learning LightPod, try to understand why this algorithm works. But we are getting ahead of ourselves. Let's first display the algorithm. So it goes as follows. We have these 3 steps. So Sergio, what are these 3 steps? What do they mean?
So these 3 steps are the typical that one always looks or sees when you look PCA in Google. Yeah, you first have to do basically a data normalization. Yeah, you want to have your data centered around the mean, so centered around 0. Basically, that's why you subtract the mean. And you want also to divide by the standard deviation of the corresponding data such that because, for example, if you have some data that have different units, yeah, you don't want them to have more influence on your decision just because they have different units, yeah. So you want to somehow normalize also that data.
Right, makes sense.
Okay, the second step that we have here would be the computation of the covariance of that data, that you can basically here have like a mean of the data and you compute the covariance using the multiplication of the data matrices here, okay,
Right.
of the scaled version of the data matrices.
Right.
Okay.
And then the last step?
And the last step is one that you have learned also in linear algebra before, is basically SVD decomposition, okay, a singular value decomposition. So we can write our covariance matrix in this form. This is a singular value decomposition.
Right.
Okay.
So in this way, we have now pre-processed the data for PCA, and then comes the important second step, and that looks like this. So can you explain to us what's going on here?
Yes, exactly. So what we can achieve now with this is we are going to achieve a new coordinate system yeah, that we are going to denote with these PC sub-indices here. And this coordinate system is basically described by the eigenvectors that you have in this matrix V. Okay, so what we want to is we want to transform the original data points without scaling them, just rotate them. Yeah, and you can do this by multiplying your data or your scale data points with basically these eigenvectors. Yeah,
Right.
You are just rotating the data points to the new coordinate frame defined by the eigenvectors. Okay, so
And-
this is the first step.
Yeah, and at this point, we have not done any dimensionality reduction yet, right?
No.
It's just a different representation of the same data, no loss of information.
Exactly. We are just rotating the data. We are just doing a transformation of the coordinate system, but this still has the same dimensions. Yeah. So we still have here the same amount of data points of features that we could be describing in that data.
Right. So where do we get the compression from? I guess that's the second part of this equation.
Exactly, that's the second part of this equation, and this is what you have here, yeah? You have here in XC, that's the data compressed, that's why we use this C sub-index, yeah? And we want now to have a compress a dimensionality reduction. Yeah, that's the goal of PCA. So how do we get it? Well, we get it in that we multiply this scale data, not with a matrix that contains all the eigenvectors, as we did before, but with a matrix that contains just an R number of eigenvectors, where R is smaller or equal than N. Yeah, and in this way, we are going to obtain, we have just less features on our data. Okay?
Right. So to bring this back to the example that we have seen here, basically here we have decided we just want one principal component. So the compression goes from 6 to 1, which means that R is equal to 1. And consequently, the values in this vector V1, they are the values that we see here, correct?
Exactly, yeah. So what we would have is that this matrix V, yeah, this matrix V then basically has as each one of the columns the different eigenvectors, okay? And then, as you said, in this example, we would have only, we choose that as R here only R equal to 1. So we are interested only on having one eigenvector doing the compressed representation.
Right.
Yeah? And in that example, this V1 is the one that would be exactly 0.5, 0.5, 0.4,
0.1, and 0.3. Yeah.
and 0.3. Yeah, exactly those linear factors that we see there. Yeah,
Right.
That's what we really want to achieve at the end. This is going to make the compression in our space of having only one feature instead of having 6 features at the beginning.
Okay, so this is the algorithm of PCA, and we can just apply it as if we are cooking from a recipe book. But the question now, and that is what we want to discuss, is why does this make sense, right?
Exactly, yeah, that's the point. That you might have learned this, yeah, why do I do an SVD representation here? Why is the eigenvector actually a good way to compress our data?
Yeah, it's not clear from this.
It's not obvious, yeah. This is what we really want to discuss now. Why does it make sense?
Exactly.
Okay.
And for this, we are going to the next slide now, and we are going to look at a much simpler example with just 2 features, which are x1 and x2. And we have some data points that we can see here. And we can see, for example, again, it's a setting where dropping one of the dimensions would be a bad idea, because we have lots of variation in both of the dimensions. But what we can also see is that there is clearly some correlation between our 2 features. So clearly, as x1 is increasing, we also have that x2 is increasing. So it's a good case study for PCA, where out of our 2 dimensions, we want to then just have 1 dimension.
Exactly,
Correct?
yeah. And as we said, we cannot do it directly, yeah. We cannot just drop x2 because x2 is varying a lot, yeah. Just looking at the component x1 of each one of the data points, you are losing a lot of information. But is there some combination, as we've done before, that would allow us to have a good compression with only, or a good representation of the data with only 1 component? Yeah?
Right.
This is what PCA is about.
Right.
Okay.
So we start with this data. And as you said before, we now apply a transformation with the matrix V. And this transformation should be a rotation.
Exactly.
And in this case, it would look something like this.
That's it.
And why have we chosen such a rotation?
Yes, so we have chosen such a rotation because here you see that now the variances on the data points are basically almost exclusively appearing on this first axis, yeah? While in the second axis, they are all around 0. Of course, there are some variations because it's only a transformation, but you see that now if you just look at the x component of those data points and not at the y component, yeah, you have a pretty good representation of the full information of the data point because the y component is almost 0, yeah, so you are not losing basically almost any information. Yeah?
Right. And just like before, what we have done so far is again not a dimensionality reduction, it's just a transformation, so it's the same amount of data. It only becomes a dimensionality reduction as soon as we, as you just said, basically drop the information of this second PC axis.
Exactly, yeah. So as you said, this is just a for the moment, this is just a transformation. We take the original data, we multiply it with some vectors v, and now we want to do the compression, as you just mentioned. Yeah, we want to do from this data point, for example, we want to look only at its x component, at this first component. Yeah. And we would consider then this data point, yeah? And this data point, it's already XC. That's a compressed version of the data in which we are looking only at this X component of each data point. And this is already a compression because now we have only one dimension, yeah? We have only the value in this axis is described in that compressed part of the data. We can describe it mathematically as we also wrote here. The compressed data is then the original data, the scaled version of the data, multiplied by maybe just the first eigenvector or the first vector v1. Okay, and this is basically what we have described before, but now also seen graphically.
Yeah. Okay, yeah, this all makes sense. It's really just basically another graphical representation of what we have done. The question is now, okay, we can get these v vectors from the singular value decomposition, but that's not what we want to do now. We want to derive how to get these vectors from a more intuitive approach. And that approach, how do we go forward with that?
Exactly, yeah, so the question is, I mean, what should this vector v be? Yeah, we know from the algorithm it should be the eigenvector, but why is this happening? Okay, and this is what we are going to try to think now. And let's just think, okay, what is what we want to achieve with this vector v? And there are basically two conditions that we want to achieve with this vector v. Okay, we want basically these vectors only to rotate the data, and we want that the compression error, or the error that we obtain with the compression, is minimal.
Okay.
Okay.
And this compression error, I mean, it's quite visible what it is here. So it's basically the difference between the original point and the new compressed point, which we can also express now, for example.
Exactly.
Correct? So it looks like this. Basically.
Exactly. This is how the error would look like, is the difference between the exact but rotated data point and its compressed version. That's the error. We would like, of course, to have this rotation such that this error is minimized for all data points. Looks like a reasonable goal. This is really what we want to achieve. Okay, and the question is, why does the SV decomposition achieve that?
And I guess we can also express this error in just a single number, basically, and this number looks like this, right?
Exactly, yeah, so we can say that the error, the norm of the error squared, if we want to consider squared norms, it's just basically the difference between the exact but rotated point x, and its compressed version, so this is basically the length of this line, okay? That's the error.
Yeah. Should we quickly summarize what we want from our transformation so that it becomes clear to the audience again?
So from our transformation, what we want is we want to achieve two things, The first one is that we want that our transformation does not scale, does not change the data, but it just rotates it. So how can we describe this mathematically? We can say basically that the norm of this vector, and let's consider now for the moment that we have this setting here, and therefore we are looking only for one eigenvector because we want to reduce from 2 dimensions to 1 dimension. This, of course, works also for more dimensions, but to make the math simple, we will consider this data. This case, okay? So let's imagine we say, okay, this v1, the norm of this v1 vector has to be equal to 1, okay? Why that? Because this makes the vector unitary, and therefore it is not scaling or stretching the data, it's gonna only rotate it.
Okay, so that is the first condition. The second condition is related to the error, I suppose.
Exactly, What we have said is that what we want to do is we want to minimize the error that we obtain, that we actually achieve in this compression for all data points.
Right. So for all data points, it would look like this, basically.
Exactly. But so if we write mathematically this, what we really want to achieve, if we talk, for example, in the terms of cost function, our cost function, would be here something that depends on v1. We call it j. Okay, and we can write this, what we want to minimize actually is the average sum of errors over all data points, So we want to minimize here over all data points the norm of the errors, square norm of the errors that we have obtained here. Yeah, so this is just doing the average basically. One could use m-1 or m. Typically in PCA, one uses m-1 to do the average. And here we just add up these errors for all data points. Okay?
Right.
So those are these two conditions that we really want to achieve. We don't want to change the data with the transformation. We only rotate it. And we want to have the transformation that has the minimum compression error.
Makes sense. Now I see a problem because, okay, this is intuitively correct, of course. But if I look at the equation now, I see here already the compressed data, which we would obtain by applying the transformation with this v vector. So how can we get this? I guess this is a problem.
Exactly. What we need now is we need to somehow be able to write the error in terms of our vector v1, the one that it's going to do this rotation, because then we would like to solve an optimization problem that's so that we can choose v1 such that this error is minimized. Yeah, but how does the error depend on v1? Yeah?
Right.
This is not clearly seen here because this depends on, as you said, for example, the compress and the PC data that depend on v1 in some form. Yeah?
Right, right. But there's a trick that we can apply, which comes from some geometric interpretation, right?
Exactly.
So we can display this trick in this way. What does this tell us?
Yes, so this is something you all know from high school, yeah, or even before. This is the Pythagoras theorem. It basically, as you may remember, yeah, so the longest side of the triangle square is equal to the length of the other, of the sum of the squares of the length of the other sides, yeah. Mathematically, you can write it like this, yeah. And with the help of the Pythagoras theorem, we can actually find the relationship between the error and our vector v1. Okay?
Right. But, okay, so the idea is that we have here as the yellow error, we have the compressed data, basically, the length of that. Here in white, we have the error, which we are interested in as well. And here we have the PC1 component, but for the uncompressed data, right?
Yes.
And this helps us that this quantity here appears, correct?
Yes, this helps us because this quantity is going to be constant. It doesn't matter actually which vector v we choose. This will always be constant because our vector v, because it is unitary and it's not performing and scaling, this vector will always have the same length. Yeah, what we are doing, depending on which vector v1 we choose, we are rotating this in one way or another, but the length of this vector will be constant. Yeah, so the length of this vector, this will be some constant that we can call c tilde, for example.
Right.
Okay.
And with this knowledge, we can now basically write the equation that is shown here. Can you elaborate that a bit?
Yes, so we can write this equation for all data points. We add up this equation basically, okay? And then this is what we could have here. So we have here the average error, yeah, for all data points. That's the only thing we are doing here. We will have, if we add up this part here, yeah, for all data points, we would have just some constant because each one of the parts for each one of the points, it's a constant, so it will be a constant, yeah? And then we have here, if we put this part here with a minus on the right-hand side, yeah, for the compressed part, then we would have the average length for each one of the data points. Yeah, so this is all that we have done here. And now, one important thing is that you see here we have the average data point, the average error, yeah, and this is what we had here in the cost, yeah. So it will be interesting to see how this actually can be transferred here, such that we obtain in our cost function our vector v1 that is going to do the transformation.
Right. And now as a next step, we basically exploit what we have written here at the very top, right? That we can express the compressed data for all data points in this matrix vector multiplication. And this
Exactly.
leads to the following reformulation, which is now shown here.
Exactly, yeah. So here we just continue reformulating this part on the right-hand side, and we still have the constant, yeah. And here, instead of having the compressed data, we just have here, yeah, the compressed data is just the original data multiplied by the vector v1. That's exactly what we have written here, okay? And then here, what we have written is that well, we can just formulate out this norm. Yeah, this is just the norm square, and if you have this for a matrix vector product, you can write it like this. Okay, this is just linear algebra. You can write it like this. Okay, good. And now, if you also have a look at a point here where you look at how we had defined the covariance matrix, you can see that this is exactly the part of the covariance matrix. Yeah, so you can substitute here the covariance matrix, so you have the constant and then just minus the eigenvector covariance matrix eigenvector.
Right.
Okay?
So this helps us now because we have reformulated basically an expression for this cost function, which we could not explicitly express in terms of V1 until now, but suddenly we can.
Exactly.
So how do we write this now?
Yes, so what we can do now is we can try to write an optimization problem, yeah, and to see this is really what we want to achieve when we do PCA, okay? And let's try to write this optimization problem. This optimization problem would look something like this, yeah? We want to minimize, our degrees of freedoms are the eigenvector, in this case only V1. We want to minimize the cost function, yeah? And the good thing is that we can write now the cost function as a function of V1, yeah? So the cost function, if you look at this formula here, yeah, the error here, we can substitute with this part, okay? And this is exactly what we are going to do. So we want to minimize minus, a constant that is not going to affect the solution of this minimization problem, minus V1 sigma V1 transpose here, okay? This is our cost function of the optimization problem. And then we have another condition that we want to achieve. We can write this as a constraint, yeah? So we say subject to the norm of V1 square should be equal to 1, okay?
Right. So this is the optimization problem we now want to solve to obtain the vector which gives us the compressed representation of our data, which minimizes the squared error, basically.
Exactly.
How do we solve this?
Yes, so this is a constraint optimization problem, so we can solve it easily if we just compute the Lagrangian. If you remember about optimization theory, you compute the Lagrangian, you apply conditions of optimality, and we can solve it. Yeah, we can do this very easy in this case because it's an equality constraint problem. So let's write the Lagrangian. Yeah, so we write the Lagrangian. The Lagrangian is then a function of the optimization variables, which in this case it's only V1, and our so-called Lagrange multiplier for this constraint, let's call it lambda, for example. The Lagrangian is just the cost function plus the Lagrange multiplier multiplied by the constraint. That's all what the Lagrangian is. So we can write the Lagrangian and we would obtain this. We can leave the constant out, okay, because this is not going to affect the optimization, the solution of the optimization problem. So we leave the constant out, and then we would obtain just basically minus V1 sigma V1 transpose and plus lambda multiplied by the constraint. Yeah, we write the constraints in the standard form, so we would have here the -1 at the other side, and we can write also the norm as a product vector. Yeah, in this case, as a scalar product, V transpose V. Okay.
Right. So this is the
so
Lagrangian.
-1. Sorry. Yes.
Oh yeah. Correct.
And the constraint. This is the Lagrange. Okay.
Yes. So, okay, you said this is the Lagrangian, and then the next step was to apply the conditions of optimality, which basically means the Lagrangian, the derivative of the Lagrangian with respect to V1 has to be equal to 0.
Exactly, yeah. So if you remember from optimization theory, yeah, the derivative of the Lagrangian with respect to V1 should be equal to 0. So what is the derivative of the Lagrangian with respect to V1? Well, you can do the derivative of this part, yeah. It's a derivative with vectors and matrices, so maybe it's not so easy, but this is like a V square, okay, so as a V1 square, so you can write it like this. It could be -2 V1 transpose, and then multiply with sigma. Okay, that would be the derivative of this first part. The derivative of this part then would be similar as before. We have also the square, so the lambda is a scalar, so you can actually write it wherever you want in the multiplication. So you would have here plus 2 lambda V1 transpose. Okay, and then the condition of optimality says that this should be equal to 0.
Okay, yeah.
Okay.
So now we have a condition that we need to satisfy for V and lambda, but it doesn't seem straightforward to solve yet. how can we proceed from this point?
Yeah, so we can have a detailed look at this equation. Okay, this is what is going to tell us. Okay, which condition do the optimal solutions of this optimization problem have to fulfill?
Yeah.
So we can say, okay, well, this 2 is at both sides. We can basically divide by 2 on all sides, and this would go away. And then we can rearrange a little bit this equation, and put on the other side, or basically put the negative part on the other side, and we can actually get to this equation. We have sigma v1, which would be this part. If you can flip actually the multiplication with transpose, because sigma is a symmetric matrix. And we have on the other side lambda v1. Okay? You can just rearrange a little bit and get to this equation. So this equation maybe reminds you of a typical equation that you have seen before.
Right, yeah, it looks very familiar. I mean, just to recap, we have here a matrix, which we multiply by a vector. And this should be equal to some scalar, which we multiply by the same vector. So it's quite literally just the equation that we have to satisfy for an eigenvalue-eigenvector pair.
Exactly, yeah? And this is going to be useful because, well, in this case, because we are actually dealing with symmetric matrices with positive eigenvalues, then these eigenvalues are actually the same as the singular values that we would have in this decomposition, okay? So in this decomposition, we are having these eigenvectors and the eigenvalues. So we know directly that the vectors that are actually minimizing or solving this optimization problem, are eigenvectors of this matrix.
Right.
Okay? And this is the reason why we actually, or why it is reasonable to use the SVD decomposition here, because these eigenvectors are actually, together with its corresponding eigenvalue, they are the ones that are solving this optimization problem, which means they are minimizing the error, and that's basically the key point here.
Right. But there's still an issue, because, I mean, with a matrix as we have it here, we would have 2 eigenvectors and 2 eigenvalues. So the question is, which one should we choose?
Exactly. So again, consider only this simple case in which we have 2 and we just want to choose one. The same could also be extended for more. But this gets more lengthy to explain. We have basically 2 choices. We can choose the eigenvector associated to the largest eigenvalue, or the eigenvector associated to the smallest eigenvalue.
Right.
Okay.
Yeah.
And what we can do is let's have a look at what we would obtain. So if we choose a certain eigenvalue, one of the eigenvectors, maybe the largest one. We have its corresponding eigenvalue, which is the largest one. And the corresponding eigenvector. If we multiply basically by V1 transpose to both sides,
From the left.
From the left, we would obtain this. The lambda can be whenever you can put it whatever you want, because it's just a scalar. We would obtain this here, okay? Now, we know that this part here is going to be 1, because this is just the norm of the V, okay? And this is basically what we could obtain, We obtain that basically this term here is equal to the eigenvalue.
Right. And this term here is important to us because we have seen it before. It basically just shows up here.
Exactly.
But importantly, with a negative sign.
With a negative sign.
So what does that mean for us here?
What does it mean? It means that if you choose here the largest eigenvalue, this term will be very positive. This means this term will be very positive, and with a minus, it will be very negative. And what we are trying to do is we want to minimize the error. We want to minimize, and therefore, what we would like to, if we have this choice between the eigenvalue, the eigenvector associated to the largest eigenvalue, and the eigenvector associated to the smallest eigenvalue, we want to choose the eigenvector associated to the largest eigenvalue, because this will give us a smaller error.
Right, that makes sense. We have actually prepared 2 images of that so that it becomes a bit more clear. So here we see what happens also in the original space of the data if we choose our V according to the largest eigenvalue.
Exactly. And you see that here the errors sure. This is basically the same image that we had before on the original form, yeah. And you see that, well, the errors are small, yeah. And these are basically actually the smallest ones that you would get with only one feature and a linear combination of features.
Yeah, and now if we choose the second largest eigenvalue, or the second eigenvalue because there are only two, then what would happen is we would get this fit.
Yeah, and those would be the errors. Yeah, you see these long lines. This is telling you that you have large errors here. Okay, so of course, if you want to choose the other data compression. Okay, this is again only for the case of 2 dimensions. Yeah, when you have 10 dimensions, maybe you want to get just the first 3 eigenvectors. Okay, and that's why the SVD decomposition is useful, because in this S matrix you are going to get always they are by default always ordered in descending order, so you choose the first vectors, and that's why we wrote it also like this. You would choose the first eigenvector, R eigenvectors, and they will go from largest to smallest, and they will always tell you these are the best possible eigenvectors you can get.
Right. Okay, so now we have achieved what we wanted to achieve. We have established an intuition of why PCA makes sense for the kind of problem that we are trying to solve. It basically boils down to this equation, or more specifically this equation. We want to minimize the error after the compression, and importantly, we have established this connection of minimizing the error to solving an eigenvalue, eigenvector problem, which in this particular example is similar to solving the SVD problem.
Exactly, yeah. And that's really the important reason. Why do you have to do an SVD decomposition when you do PCA? Because those eigenvectors are actually solving this optimization problem. Yeah, they are the eigenvectors that lead to the minimum error.
Right. I guess there's nothing else to say about this topic. So thank you very much for listening to our podcast, and also thank you again to Sergio for explaining the topic to us, and we hope to see you all in the next episode.
Thank you very much. See you next time.
Bye-bye.
Bye-bye.